Hi, Sterling Allen here. I'm at David Yurth's house in Salt Lake City. He's going to be talking about a Nova Neal compression engine and how that works and why he's open sourcing it. So here we go.
Hi, Sterling. In 1936, an inventor by the name of Robert Neal obtained a patent from the United States Patent Office for an engine whose medium of exchange was compressed air, which was self-sustaining once it had been started. His patent application was initially denied because perpetual motion was a category of application that the patent office had decided they would not respond to. So, as the story goes, Mr. Neal packed up his engine, took it to Washington, put it on the desk of the patent commissioner, turned it on and demonstrated it, after which he got his patent. The story about what happened to the engine is a matter of record, and eventually, because of interference from people who wanted his engine and who kidnapped his daughter as a way of compelling him to relinquish it, he agreed that he would disassemble the engine and distribute the parts and not make it anymore. In the 75 years since that happened, to the best of our knowledge, no one has succeeded in either identifying the specific set of principles that made it work or recapitulating the engine in a newer or similar kind of design. After about 10 years of research on this process, we know how his engine worked. And we understand the principles that are involved in what we have available today in 21st century technologies and materials to operationalize what he created out of much cruder materials a long time ago. The engine operates as a heat exchanger. There's nothing exotic about it. What happens in his engine is this. Two secrets made it possible for him in his design to build a self-sustaining heat exchange air compressor engine. The first is that he developed a valve that enabled him to put low pressure air into a high pressure tank. And the second thing he did was to design his engine so that the first air that went in was recompressed to a higher pressure, and the tank that he accumulated the pressure in was designed and equipped so that he could retain the heat of recompression. What that meant was, based on the calculations that we've developed today, is that 100 psi air input into his engine at 20 cubic feet per minute was translated into a much higher pressure that allowed him to tap the same input volume but at a self-amplified pressure that was 8 to 12 times higher than the original input value. It's just as simple as that. So what we've done is put together an abstract that details the principles that make it work, a partial list of components that are needed in order to build one today, and the sources for the pieces that accomplish the things that made his engine unique. Essentially what happens is that we take a tank of about 100 gallons. The tank is a serious piece of business. You have to make sure when you're operating at pressures in excess of 11 to 1200 psi that you haven't shortcut anything on your tank. You can't afford to fool around with those kind of pressures because they're not trivial. One end of the tank has to be detachable. The dome has to be detachable because the recompression equipment goes inside the tank and has to be contained in it in order for low pressure air to be input into an internally held air booster while the heat of compression is retained inside the tank. So if a Haskell booster or a booster made by Eaton or other manufacturers, ubiquitously available on the internet, they use them in the space station, you can buy them quantity one for anywhere from $2,500 to $5,000. These are typically the kinds of devices that are used to take air pressure from a conventional single or double cylinder compressor and convert that into 4,000 psi pressure in scuba tanks. We're just going to put one of those inside the tank and seal it up, make sure that the tubing and the piping is pressure rated so that it isn't collapsed under the internal pressure of the tank. Once that is put together and engineered, then you have a compressor on the outside of the tank, which is driven by an electric or a gasoline powered engine and connected by a slip clutch of some kind, so that once the engine becomes operational from the tank, you can disconnect the compressor from the extrinsically powered unit and drive it by an air powered engine, which takes air off the tank out through the dome. We've specified a DiPietro engine. We like the DiPietro engine because it has a rotating cylinder. It operates with very high torque and very high efficiency at a relatively low consumption rate. So at something on the order of 18 to 20 cubic feet per minute, a DiPietro engine powered by a tank that is compressed at 800 to 1100 psi will enable that little engine to drive two things simultaneously. The first thing it'll do is drive the external compressor so that it's continuously recompressing the tank, but you have 40 to 45% of the work potential provided by the pressure in the tank left over to perform other kinds of work. So the DiPietro engine then can also be attached to a compressor or an alternator or a generator or a pump or anything that requires shaft-driven torque in order to perform work functions. The reason this apparatus works is because the air that is put into the tank at 100 psi initial value, without the use of any external, extrinsic, mechanical, or electrical power, is driven through the internal recompressor, which operates by cams. That's what allows you to put low pressure in to a tank that's repressurized now to about 800 psi. By retaining the heat of compression, the 800 pound per square inch pressure coming out the end of the recompressor is further amplified so that you have a compressed tank at 11 to 1200 psi at whatever the ambient temperature is inside the tank. If you paint that tank black and sit it out in the sunshine, you'll get an incremental amplification of between 25 and 40% in addition to the retained thermal value that is retained from the compression. So this engine would cost you between $7,500 and $10,000 to build one of these things using ubiquitously available off-the-shelf materials. When you put this thing together, you should have a good heating, ventilating, and air conditioning or refrigeration guy help you make sure that your connections and your tubing and the other interstitial pieces of your apparatus are going to be able to withstand the pressures, and so that you don't introduce leaks and other kinds of anomalies into the system. We're releasing this information. We've done the calculations, we've tested all the pieces, we're in the process of building a demonstration engine now. We hope to be able to bring that with us to the next Tesla convention in Albuquerque in 2014. In the meantime, we're open sourcing this design. The reason I'm doing that is because I want the design to be in the world. I don't own it, I didn't create it, I understand it, and I'm willing to share it with anybody that wants to build it, with absolutely no charge and no strings attached. If you want this information, it's ubiquitously available. Sterling's going to publish it on the wiki site. You go there and download it. If you want to correspond with me about what to do and how to do it to make it work, I'd be more than happy to entertain your calls or your inquiries, but there are no fees, there are no charges, there's no strings attached. If you build it, you own it, and more power to you.
On the system you were describing that would cost $7.5 to $10,000 for materials, what would be the output of that?
Somewhere between 45 and 48 kilowatts continuous.
45 kilowatts?
Yes, sir.
Wow.
With 100 gallons.
Would you care to talk about some of the other stuff you're doing, or is that off the record for now?
We'll do another tape about another application. application in about 60 days.
Okay.
Okay.
Thank you, David.
You're welcome.
Why he's open sourcing it. So here we go.
Hi, Sterling. In 1936, an inventor by the name of Robert Neal obtained a patent from the United States Patent Office for an engine whose medium of exchange was compressed air, which was self-sustaining once it had been. The commissioner turned it on and demonstrated it, after which he got his patent. The story about what happened to the engine is a matter of record, and eventually, because of interference from people who wanted his engine and who kidnapped his daughter as a way of compelling him to relinquish it, started. His patent application was initially denied because perpetual motion was a category of application that the patent office had decided they would not respond to. So, as the story goes, Mr. Neal packed up his engine, took it to Washington, put it on the desk of the patent.
Hi, Sterling Allen here. I'm at David Yurth's house in Salt Lake City. He's going to be talking about a Neal compression engine and how that works. And
he agreed that he would disassemble the engine and distribute the parts and not make it anymore. In the 75 years since that happened, to the best of our knowledge, no one has succeeded in either identifying the specific set of principles that made it work or recapitulating the engine in a newer